You live in a universe with a hard speed limit, and that single rule is one of the main reasons you will probably never meet aliens. That limit is the speed of light, about 300,000 kilometers per second, or roughly 186,000 miles per second. In physics, this number is not just how fast light goes, it is the maximum speed at which any cause can affect any effect. This means there is a maximum rate at which the universe can update itself. When something changes here, the rest of the universe only finds out about it at or below this speed. No news about supernovae, no change in a star's gravity, no artificial signal from an alien transmitter can arrive faster than that. The structure of space and time itself is built around this limit. In technical language, we say the speed of light is invariant. It is the same for all observers, and everything else, from time dilation to length contraction, bends around that rule. So why can't you just keep pushing a spacecraft harder, stack more engines, burn more fuel, and keep increasing speed past that limit? Special relativity blocks you. As an object's speed, measured as a fraction of light speed, gets high, the energy you have to add for each extra bit of speed rises very fast. From your point of view, the moving object gains more and more kinetic energy, its internal clocks slow down and its resistance to acceleration grows. People sometimes call this relativistic mass increasing, meaning that the object behaves as if it is getting heavier, even though you are not bolting extra material onto it. At everyday speeds, this effect is so tiny you can ignore it. A car at 100 km per hour or a jet at 900 km per hour is moving at a tiny fraction of light speed. So Newton's simple laws work fine. But push a spacecraft to 10% of light speed, 0.1 c, about 30,000 kilometers per second or 67 million miles per hour, and relativity starts to matter. Push it to 90% of light speed, 0.9 c, and it dominates. The kinetic energy is not just 9 times higher than at 0.3 c, it is far, far, far larger because of relativistic effects. Each small increase in speed near light speed costs you an enormous increase in energy. By the time you reach 0.9 c, the energy you need for a large crewed vehicle is already way beyond current human capability. You're talking about total energies comparable to years of global power use just to accelerate, not counting braking at the other end. Going from 0.9 c to 0.99 c is even worse. It is not an incremental upgrade, it is an energy cliff. At that point, you're in a regime where only star-level power output sustained for long periods would be enough to push something massive. As you try to get closer and closer to 1.0 c, the required energy rises toward infinity. In simple terms, reaching exactly light speed would take infinite energy, which is another way of the universe saying not allowed. So just go faster than light is not a clever engineering challenge. It is a demand that the universe stop behaving the way every test and every observation says it behaves. You would need a completely different physics, not just better engines or better fuel. And that brings us to the lab evidence, because this is not just theory written in a textbook. It is something we test over and over again, with real particles moving at insane speeds. Look at particle accelerators such as the Large Hadron Collider. In those machines, we take protons and push them to energies of several trillion electron volts. In plain terms, that is a huge amount of energy packed into a single tiny particle. These protons reach more than 99.9999% of light speed. If any machine on Earth could brute force its way past the speed limit, it would be one of these. But what happens, exactly as relativity predicts, is that as you keep feeding energy into the particles, their speed gets closer and closer to c but never equals it, never crosses it. Their internal time slows relative to us, their effective inertia grows, and the beam takes tighter and tighter control to steer, but the speed stays below c. The same story shows up in nature. Cosmic rays launched by supernovae and black holes hit our atmosphere with energies even higher than what we make in accelerators. They are moving at speeds so close to light speed that the difference is tiny beyond normal intuition. Yet they still do not break the limit. We see their lifetimes extended by time dilation in the atmosphere. We see their interactions follow relativistic rules, and they never give us a hint of superluminal behaviour. GPS satellites in orbit, which need relativistic corrections to keep their timing accurate, also confirm that time and space behave exactly as Einstein's theory says, with the same speed limit wired into the math. All of this has a direct consequence for aliens. If any civilization out there is made of matter, uses fields, interacts with the same kind of particles we see, they are working under the same rule set. They can be far more advanced than us, they can understand more layers of physics, but their signals still move at or under light speed, and their ships still hit the same wall as they push towards sea. You can assume they know why the limit exists better than we do, but not that they can ignore it. Now connect that fixed speed limit to the problem of actually finding and talking to someone else in the galaxy. It is not enough that aliens exist somewhere in the universe. For there to be any realistic chance of contact, they have to be inside a certain distance from you, measured in light years, and they have to be active at roughly the same time as you. Because if their radio signal or laser flash or high-energy beacon has to crawl across thousands of light years at light speed, then you are automatically dealing with thousands of years of delay for a one-way message. Take a simple example. Suppose there is a civilization 100 light years away. If they send out a signal today, the earliest you could detect it is 100 years from now. If you respond as fast as possible, your reply takes another 100 years to get back to them. That is a 200-year round trip for a single question and answer. Push the distance to 1,000 light years, and the round trip becomes 2,000 years. Nothing about that depends on how advanced your computers are, or how clever your encoding is. It is just distance divided by the speed of light. This means the speed of light defines the size of your contact bubble. Inside their bubble, there is at least some chance of exchanging information on timescales that a civilization might be able to plan around. Outside that bubble, communication becomes so delayed that for all practical purposes, it is useless for real-time interaction. You end up trading time capsules, not conversations, and because the energy cost of pushing ships near light speed is so extreme, you can assume that actual physical travel is even less practical than sending signals. So the limit set by light speed does two brutal things at once. It stops you from sending ships or signals any faster, and it turns distance into time in a very direct way. Every extra light year is an extra year of delay, minimum, that no amount of technology can compress. When people ask why we have not seen obvious evidence of aliens, this is a big part of the answer. Even if they are there, they may be outside the region of space that can ever realistically talk to you during the lifetime of your species. And this is just the first layer of the problem. Because now that you know the fastest possible speed, the next question is simple and painful. How big is the arena you are trying to cross, even at that absolute maximum speed? How far away does something have to be before it might as well not exist? For you, for your entire species, for your entire history of technology. In space, that threshold is shockingly close, and it starts right in your own stellar neighbourhood. The closest star system to you, Proxima Centauri, is about 4.24 light-years away. In distance, that's roughly 40 trillion kilometres, or around 25 trillion miles. On paper, that is nearby, it's the closest other star you have. But now plug in a real number you actually control, the speed of Voyager 1, the fastest spacecraft humanity has ever launched, moving at about 17 kilometers per second, around 38,000 miles per hour. At that speed, reaching Proxima Centauri would take tens of thousands of years, longer than all of recorded human history by about a factor of 10. So you are already in a bad position. Before you even leave your local bubble, your best hardware turns the nearest star into a multi-10,000-year project. No culture, no language, no institution on Earth has shown it can stay stable for even a fraction of that time. You can talk about generation ships, you can talk about suspended animation, but you are already outside any experience humans have ever had. And this is for the absolute closest target, the easiest possible interstellar trip. If your best shot at visiting the nearest system looks like Stone Age plus everything since all over again just to arrive, what does that say about the rest of the galaxy? If the immediate neighbourhood is that punishing, what happens when you scale up to the structure you actually live inside, the Milky Way? Your galaxy is about 100,000 light-years across. That means a beam of light, moving at that fixed maximum speed of about 300,000 kilometers per second, still needs 100,000 years to go from one side to the other. There is no trick here, no better engine, because you are already using the absolute speed limit. So take a civilization on the far side of the galaxy. If they built a powerful radio transmitter and turned it on when Homo sapiens first appeared, a few 100,000 years ago, their very first hello would still not have arrived here yet. They could have risen, expanded, stagnated, and completely vanished, and you would still be waiting for the first edge of their signal to touch your region of space. That is why people sometimes call the Milky Way a light-speed prison. You can see many parts of it with telescopes, you can map stars and gas clouds and black holes, but seeing is not the same as talking. For any kind of two-way communication, for any we speak they answer, you are locked into this 100,000 light-year wide structure, and your signals crawl across it at a speed that turns every conversation into a multi-millennia delay. Even if you restrict yourself to just a slice of the galaxy, say a few thousand light-years across, you are still looking at thousands of years for a one-way message. Inside that structure, physical distance and light speed delay are basically the same thing, and that is just inside your own galaxy. What happens when you step outside it and look at the next big island of stars in your region of the universe? The nearest major galaxy, Andromeda, is about 2.5 million light-years away. In simple terms, that means any signal they send you today, travelling at light speed, arrives 2.5 million years from now. When that message finally gets here, assuming anyone is still listening, your species may have changed, your continents may look different, your climate may have gone through several extreme cycles. 2.5 million years is the kind of timescale where, on Earth, you get new species of mammals. It is not remote communication, it is a completely different geological and evolutionary era. So when people talk casually about galactic empires spanning multiple galaxies, the numbers quietly kill that picture. A message from Andromeda is not late by a few days, is late by millions of years. A reply from you, back to them, is another 2.5 million years on top of that. You are not exchanging ideas, you are not coordinating anything, you are dropping frozen statements into a timeline that will be unrecognizable by the time they arrive. At that scale, even light, the fastest thing allowed by the universe, is too slow to keep any meaningful link between two civilizations. At this point, the raw size of these distances starts to break your intuition. In metric, you are dealing with numbers like 10 quadrillion meters, or a 1 followed by 16 zeros, and then scaling up to numbers like a sextillion meters, a 1 followed by 21 zeros. In imperial units, you can say things like 100 quadrillion miles, and it still does not really land, it's just another big phrase. You can swap units all day, kilometers, meters, miles, none of that changes the core fact. Every time you divide these distances by the speed of light, you do not get inconvenient travel times, you get time scales that break civilizations. So from a contact point of view, the units are just labels. What matters is that the Milky Way is on the order of 100,000 years wide at light speed. Andromeda is millions of years away at light speed, and even your nearest star is tens of thousands of years away at current spacecraft speeds. Those numbers are lethal for any idea of real-time alien contact. You need overlapping windows of time, overlapping regions of space, and a lot of luck, just to get a single exchange done before one side changes beyond recognition or disappears. This is why when you start combining light speed with distance, the search for aliens becomes less like looking around a crowded room, and more like trying to send one postcard across whole geological eras. Even if everyone is trying their best, the gaps in both space and time are so huge that almost all possible pairs of civilizations will never manage a live connection. They can watch each other's ancient light, they can see each other's galaxies, but they cannot talk in any normal sense of the word. And there is another layer of this that makes everything worse, because distance does not only create delay, it also means you are never looking at anything as it is right now. Every light year you add is another year you're looking into the past, and that time offset quietly sabotages your chances of catching another civilization in the act of being detectable, the same time you are. How can you seriously search for anyone out there when you never see the universe as it is right now, only as it was? Every time you look up, you are not seeing live footage, you're looking at delayed broadcasts. Even with something as familiar as the sun, you're already dealing with this. The sun is about 150 million kilometers away, around 93 million miles, and light takes about 8 minutes to cross that gap. So every time you look at it, with proper protection, you're seeing the sun as it was 8 minutes ago, not as it is now. If the sun magically vanished this instant, you would still see it shining in the sky for 8 more minutes, and Earth would still feel its gravity for that same delay. Stretch that idea out a little. Look at Proxima Centauri, the nearest star beyond the sun. It is 4.24 light years away, which means the light hitting your telescopes left that star 4.24 years ago. You're always seeing it more than 4 years in the past. Push out to a galaxy 1 billion light years away. Now the light left that galaxy 1 billion years ago. Back then on Earth, multicellular life was only starting to become complex and interesting. So that nice galaxy picture you see in a documentary frozen on your screen is not a snapshot of right now in that galaxy, it is a fossil, 1 billion years old. This is why in cosmology, people say that looking out is the same as looking back in time. The farther away something is, the older the light you receive from it. Distance measured in light years is literally also a time delay measured in years. At a few light seconds or light minutes, the delay is small enough that your brain accepts it and moves on. At light years, millions of light years, billions of light years, that delay becomes the dominant fact. You never get the present state of distant objects, you only get their history. Now connect that to the big telescopes. Instruments like the Hubble Space Telescope and the James Webb Space Telescope point at extremely distant galaxies billions of light years away. Because of that, they are showing you those galaxies billions of years ago. We have images of galaxies with redshifts greater than 10, which corresponds to just a few 100 million years after the Big Bang. In metric time, that is maybe 300 to 500 million years after the universe began, in a universe that is now about 13.8 billion years old. You are seeing baby galaxies, forming stars in chaotic bursts, in a universe that was denser and hotter than it is now. Whatever those galaxies are doing today, in this actual moment for them, is completely unknown to you, because their current light has not had time to reach you yet. It is still in flight, crossing billions of light years of expanding space. Any planets in those galaxies, any biospheres, any civilizations are also hidden behind that delay. You can say, there could be aliens there now, and you might be right, but you have no way to see their present. You're stuck with their deep past. Cosmology at this scale is less like a live stream and more like walking through a museum of old photographs. This time delay has a really sharp consequence when you start talking about aliens and signals. Picture a civilization 500 million light years away. That is a large but not insane distance on cosmological scales. Say they built radio transmitters and started broadcasting last year by their own clocks. They exist, they are real, they are doing science and engineering and culture right now, but the first photon of their first signal will not reach Earth for 500 million years. Your observable universe in practice includes their past, not their present. They are in your universe but not in your now. The speed of light slices the universe into layers of time around you. Nearby stars are only years in the past. Nearby galaxies are millions of years in the past. Very distant galaxies are billions of years in the past. Aliens can occupy those layers at different distances and different times, but your ability to detect them depends on whether your own moment in history lines up with the delayed arrival of their signals. If the timing does not line up, They can be shouting with huge transmitters, and you still see only silence because their shout has not arrived yet or passed by long ago before you were here to listen. This is where the idea of a search cone becomes important. Since around the early 20th century, Earth has been leaking strong radio and TV signals into space. Call it roughly 100 years of powerful broadcast. Those signals expand outward at light speed, forming a sphere of detectability about 100 light-years in radius around Earth. In distance, that sphere has a radius of around 950 trillion kilometers, about 590 trillion miles. That sounds huge in everyday terms, but place that bubble inside the Milky Way, which is about 100,000 light-years across, and it is tiny, a thin shell around one point and one spiral arm. Most of the galaxy has had no chance to know you exist yet. The vast majority of stars and their possible planets are outside that 100 light-year radius. Even if some alien astronomers on the far side of the Milky Way are extremely advanced and very motivated, the earliest they can pick up Earth's radio leakage is many thousands of years in their future. From their point of view, if they look at Earth right now using light that left here long ago, they might be seeing dinosaurs or early mammals, or some other completely different stage of Earth's history, depending on their distance. The reverse is also true. If another civilization somewhere in the galaxy has been broadcasting for 100 years, their own radio bubble has a radius of 100 light-years around their star. Unless our two bubbles overlap in space and time, we will not detect each other. You need the right distance, the right timing, and the right sensitivity, all at once. Otherwise, their now is something we will only see thousands or millions of years from today, long after our own civilization may have changed beyond recognition, or vanished. So light speed does not only make everything far away, it also desynchronizes the universe. You and any aliens are living in different time slices of each other's reality. Your telescopes are looking at their history, their telescopes are looking at your history, and the odds that both sides are in the right place at the right time with the right technology to catch each other's brief noisy window of radio and laser emissions are not very good. Most of the time, even in a universe full of life, everyone will be alone in their own now, cut off by simple distance divided by light speed. And even if you get lucky, even if your time slice and their time slice line up just enough to catch a signal, that is only the first problem. Because detecting someone once is not the same thing as talking to them, and once you try to have an actual back and forth conversation across those distances, the speed of light starts killing the idea of communication itself. How do you talk to someone when every single reply arrives after everyone you know is already dead? That is the basic reality of interstellar communication, and it hits you as soon as you put real distances and the speed of light into the same sentence. Take a nice, clean scenario. You detect an unmistakable artificial signal from a civilization 100 light-years away. You send a reply at light speed. They receive it 100 years later. If they answer immediately, their response takes another 100 years to get back to you. You finally hear back 200 years after your first hello. That is like a scientist in the 1820s sending a question, and you only now getting the reply. You do not have a conversation. You have a sequence of one-way messages separated by centuries, each one more like a time capsule than a dialogue. Now think about what a real conversation needs to function. Every intelligent communication system you use on Earth, arguments, diplomacy, scientific collaboration, even simple texting runs on feedback loops. You say something, you get a response, you adjust based on that response, and the cycle repeats. That loop can be seconds, minutes, days, maybe years for slow projects, but it is always short enough that the same people, or at least the same institutions, are involved end to end. Stretch that loop to hundreds or thousands of years, and it breaks. By the time high comes back as high back, your nations may have dissolved, your languages evolved, and systems replaced. Your descendants might not even care about the original question. This latency is not just inconvenient, it destroys continuity. You cannot negotiate treaties with a 400-year delay. You cannot co-develop science where one side has to wait 10 generations to see if the other side understood the last dataset. You cannot coordinate joint missions, joint safety protocols, joint anything. At those scales, Each message is a historical document, not a tool for coordination. Any civilization that plans on using interstellar communication has to accept that they are talking to the future, not to peers in their own era. People sometimes try to dodge this emotionally by talking about bandwidth instead. They say, fine, the messages are slow, but we can send massive amounts of information. And that part is true. In theory, you could use extremely powerful lasers focused into tight beams to send data at rates of terabits per second, trillions of bits every second. With the right optics and power, you can send blueprints, entire libraries, cultural archives, detailed instructions. Metric gives you the delay very clearly. Take the distance in light years, multiply by about 9.46 trillion kilometers per light year, and divide by 300,000 kilometers per second. Imperial lets you say hundreds of trillions of miles, but the key is this: no matter how thick the pipe is, the signal still takes decades or centuries to cross the air. So the real enemy here is not bandwidth, it is latency, the delay itself. A 10 terabit per second laser link to a world 100 light years away is still unusable for real-time chat because every file you send shows up 100 years after you send it. When they respond, their own massive data dump shows up 100 years after that. Your message always arrives in a future you do not control after your culture, your priorities, maybe your biology, have shifted. You cannot build trust, habits, or shared projects on a response time longer than your institutions can survive. Now layer this on top of what SETI, the search for extraterrestrial intelligence, is actually doing. Projects like Breakthrough Listen point radio telescopes at thousands of stars, scanning across wide frequency ranges, looking for narrowband signals that stand out from natural noise. So far, nothing confirmed, just a lot of interesting candidates that turned out to be satellites, Earth interference, or natural sources. But suppose tomorrow we hit the jackpot. We detect a clear, repeating, structured signal from a star 1,000 light years away. We decode it and find mathematics, physics, maybe even images. It is the discovery of all discoveries. Here is the harsh part. Whatever we receive is already 1,000 years old. If we answer immediately, our reply arrives 1,000 years in their future. If their civilization burns out quickly, they may already be gone. If they last a long time, they may have advanced so far that our answer looks like a museum artifact from a primitive species. This is SETI's nightmare scenario, too far too late. The silence is broken, but the timing is useless for building a relationship. We become archaeologists of their radio past, trying to reconstruct who they were from a signal that left before our own modern science even existed. In that mode, every interstellar contact is basically an archaeological dig, done with radio waves and lasers instead of shovels. You're digging into the past of another civilization's timeline, not coordinating with their present. You might learn a lot about how they thought, what they valued, how their science worked, but you will almost never be able to interact with them as a living, changing partner. They are already history by the time you hear them, and you are history by the time they hear you. So when people dream about a galactic internet, a live network of civilizations exchanging ideas and culture across the stars, the speed of light completely kills that picture. The delay is just too large. You can have records, you can have archives, you can have one-way instructions and warnings and stories meant for whoever is alive later, but you cannot have day-to-day interaction. The practical outcome is that the universe can be full of voices, and most of them will never talk to each other in any normal sense. They will just leave recordings drifting through space, to be picked up by whoever comes along whenever that happens, if it ever does. At this point you might ask a natural question. If talking across the stars is this broken, why not go there directly instead, skip the delays and meet face to face? And that is where the next layer of the trap appears, because closing those distances with a physical ship at any meaningful fraction of light speed demands energy levels that take the word impossible from a feeling into a calculation. There is a hard question you have to face at this point. If talking is too slow, can you at least go there fast enough for it to matter? When you look at actual rocket physics, the answer is almost certainly not, and the reason is simple. The energy bill explodes long before you get close to light speed. Start with what rockets can realistically do. Chemical rockets, the kind you use to launch satellites and astronauts today, throw exhaust out the back at a few kilometers per second, typically 3 to 4 kilometers per second, maybe a bit more. That is your exhaust velocity. Nuclear thermal rockets, where you heat hydrogen with a nuclear reactor and throw it out the back, might get you to around 8 to 10 kilometers per second. People talk about more advanced concepts like fusion or antimatter engines, where effective exhaust velocities might reach tens of thousands of kilometers per second, so a decent fraction of light speed. On paper, that sounds promising. But now ask a very direct question. What does it take to push an actual crewed ship to something like 0.1 c, 10% of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour? The answer is that your energy requirements do not just go up, they blow up. Kinetic energy, the energy of motion, increases with the square of your speed in normal mechanics, and relativity makes it even worse as you get closer to light speed. That means if you double your speed, you need 4 times the energy. If you multiply your speed by 10, you need 100 times the energy. Near light speed, the relationship gets even harsher than that simple square rule. So when you talk about taking a 1,000-ton ship, about 1 billion kilograms roughly, in the range of a large skyscraper's steel mass, and pushing it to 0.1 centimeters, you're in the ballpark of 10 to the power of 23 joules of energy. 10 to the power of 23 joules is not just a big number, it is comparable to decades of total human energy production at current levels. Take all the coal, oil, gas, nuclear, hydro, wind, solar, everything humanity uses over tens of years, and pour it into one burn for one starship just to get it to 1/10 of light speed. Not counting slowing down at the destination. That is for one ship one way. If you want to stop at the other end, you need roughly the same kinetic energy again to brake, unless you have some external system waiting to catch you. So now you're talking about multiple decades of global energy output tied to a single mission. And remember, 0.1 c is not some sci-fi warp-level speed. It is only 10% of light speed. At that speed, reaching Proxima Centauri still takes around 40 years of ship time, and more than 40 years as measured on Earth, because relativity effects are small at 0.1 c, so you have massive energy costs, multi-decade travel times, and you have not even touched the problem of shielding people from radiation, dealing with micrometeoroid impacts at 0.1 c, or keeping a crew alive and sane for generations. Now bring in the rocket equation, which is the basic law that links your exhaust velocity, your fuel mass, and your final speed. It says, in words, that the change in speed you can get from a rocket depends on the exhaust speed and the ratio of your total starting mass to your final mass after burning fuel. The nasty part is that this relationship is exponential, not linear. To get a little more speed, you need a little more fuel. To get a lot more speed, you need an absurd amount more fuel. For high delta V, high total change in speed, the required fuel mass shoots up faster and faster. For interstellar trips at a significant fraction of light speed, this means your spacecraft stops looking like a neat vehicle with a fuel tank and starts looking like a huge stack of fuel with a tiny payload on the tip. In metric, you can easily get into billions or trillions of tons of propellant if you try to build a self-contained rocket that carries all its reaction mass. In imperial terms, that is quadrillions of tons. You're no longer talking about launching from a planet. You're talking about mining entire asteroids or even small moons just to get enough reaction mass. Your so-called starship is basically a mobile industrial complex, a flying refinery and fuel depot that happens to carry a small habitable section. People then try to get clever and say, all right, we will not carry all the fuel. We will beam power from huge lasers in the home system. We will use light sails. We will scoop interstellar hydrogen for fusion as we go. All of those ideas run into hard limits too, either in available power, or in how much mass there is to scoop, or in how much drag you introduce while trying to collect that mass. The core point does not change. To get large, heavy objects to relativistic speeds, you pay an enormous energy cost. There is no free lunch hiding in some clever engineering shortcut, and this is not just a human limitation. Look at what nature itself does when it wants to push things near light speed. You see individual particles reaching very high fractions of C in cosmic rays, in the jets fired out of the poles of supermassive black holes, in the winds of pulsars and magnetars. To get those near light speed particles, you need engines on the scale of stars and black holes. Accretion disks around black holes convert a significant chunk of the rest mass of infalling matter into energy. That is thousands of times more efficient than nuclear fusion in stars. Magnetars have magnetic fields strong enough to rip atoms apart. These are the kinds of systems that push protons and electrons to 0.9999 C. So ask yourself, if nature itself uses black holes, neutron stars, and entire stellar environments to accelerate tiny particles to these speeds, what does it take to accelerate macroscopic objects, like ships that weigh 1,000 tons, 10,000 tons or more? Even if an alien civilization has access to stellar power, even if they build giant laser arrays or particle beam launchers, they are still bounded by the same math. The energy per kilogram does not change just because you're more advanced. The rocket equation does not rewrite itself just because your computers are better. The kinetic energy formula does not relax just because you want to go faster. You can imagine civilizations building huge beamed sail systems, using power from multiple stars to push lightweight probes to 0.2 C or 0.3 C. That is hard, but maybe just within the edge of the possible for very advanced societies, especially if the probes are gram scale or kilogram scale. But pushing entire crewed habitats with shielding, life support, structure, redundancy to those speeds is another level of difficulty. At that point, the energy cost and the infrastructure cost start to look worse than simply staying home and optimizing your own system. So you end up in a grim corner. Communication is too slow for real conversation, and travel is too energy expensive for casual visits at relativistic speeds. That is already bad, but there is a deeper frustration here. Because even when you accept all that, your brain still wants to ask, can't we just sidestep the whole problem, bend space-time, open shortcuts, use warp drives or wormholes or something that ignores distance altogether? And that is exactly where modern physics walks in, looks at your favourite sci-fi solutions and says, not so fast. You already know rockets are a nightmare. So the next move people reach for is skip the distance itself, bend space-time, jump through a shortcut, ride a warp bubble. On paper, general relativity actually lets you write down solutions that look like that. But when you look at what those solutions demand from reality, the picture stops being cool sci-fi and turns into this probably never happens anywhere for anyone. Take the famous warp drive idea based on the Alcubierre metric. The trick there is not to move your ship through space faster than light, but to move a bubble of space-time itself. You compress space in front of the bubble, you stretch space behind it, and the bubble rides along so that from far away it looks like it's travelling faster than light, while locally you never break the speed limit. In pure math, that works. In actual physics, it needs exotic matter with negative energy density, not just weird fuel, but regions of space-time where the energy of the vacuum is less than zero in a very specific way. We do see tiny hints of negative energy effects in quantum physics, in very controlled situations over very small distances, like the Casimir effect between metal plates separated by micrometers. But those are minuscule, fragile effects, not giant reservoirs of negative energy. When you ask quantum field theory, can I scale this up to macroscopic spaceship-sized volumes? The answer looks like no. Our best models give you no known way to pile up enough negative energy to support an Alcubierre bubble you could fly, especially not one big enough for a 1,000-ton ship and life support. So you end up with a metric that is mathematically allowed, but physically unsupported. You can write it in a notebook, but you cannot build it in a universe that obeys the rules we actually measure. Wormholes sound more promising at first because they come straight out of general relativity as well. You solve Einstein's equations and you get geometries where spacetime has a tunnel connecting two distant regions. Fall in one mouth, pop out the other, apparently skipping the distance in between. In a diagram, it solves everything at once, distance and delay. But once again, the fine print kills you. To keep a wormhole throat open and stable without it snapping shut or pinching off instantly, you also need exotic matter with negative energy density. You need it arranged in precise, stable configurations, resisting enormous gravitational stress. Even if such microscopic wormholes exist at the quantum level, they are likely tiny near the Planck scale, far smaller than a proton. There is no evidence in observational cosmology of huge ready-made tunnels linking star systems or galaxies. When we map large-scale structure, galaxies and clusters and filaments over hundreds of millions of light-years, the universe looks continuous. You see voids, walls, streams of galaxies, but not obvious shortcuts. Gravity lenses light in ways we understand, matching the mass we see and the dark matter we infer. If there were a whole network of massive traversable wormholes bending light and matter in strange ways, our sky surveys would look wrong. They don't. Then there is the deeper problem, causality. Relativity is built around the idea that cause comes before effect in a consistent way in all physical processes. Faster than light travel in any form lets you set up situations where that order can be broken, at least in some reference frames. You can construct what physicists call closed time-like curves, which are basically paths in space-time that loop back on themselves. Follow the path, and you end up in your own past. Now you're in full time travel paradox territory. Send a message that prevents itself from being sent. Change an event that is your own cause. All the classic kill-your-own-grandfather scenarios, but now inside the same mathematical framework that handles GPS satellites and gravitational waves. Every experiment we have in particle physics, every observation of high-energy cosmic events, lines up with a universe that respects causality. Signals do not show up before their sources. Detectors do not see effects without a consistent chain of causes. Quantum mechanics has weird correlations like entanglement, but even there, when you track actual usable information, it never outruns light, and it never lets you send data into your own past. That strongly suggests that nature is not just mildly resistant to FTL, it is aggressively hostile to anything that would allow signals or objects to move outside the light cone, the region of space-time that light can influence. Now bring aliens back into this. If some civilization had actually solved FTL travel or communication on a large scale, the consequences would not stay hidden on their home planet. Faster-than-light ships and signals would leave marks on the universe. You would expect to see matter apparently changing velocity without normal reaction forces, trajectories that do not match gravity and standard propulsion. You might see signals arriving from astrophysical events before those events are visible in light or neutrinos. You could see energy flowing in ways that break conservation expectations, because causality violations often go hand in hand with strange energy bookkeeping. Instead, what do we see? Pulsars ticking with incredible regularity, matching models of rotating neutron stars. Gravitational waves arriving from black hole mergers in perfect lockstep with the light and gamma rays at the same C we measure in the lab. Particle showers in Earth's atmosphere from cosmic rays that fit our standard high-energy physics. GPS working only because we correct for relativity, not because relativity is being broken. Across all these tests, from kilometers to billions of light years, the speed of light shows up as the same limit, over and over again. If FTL were common, or even just used occasionally with huge energies, it would be very hard to hide on cosmic scales. You would get patterns in timing data, distortions in pulses, mismatches between different messengers, light, neutrinos, gravitational waves that would scream something is outrunning light somewhere. So far, every high-precision measurement says the opposite. The universe behaves as if C is absolutely sacred. That does not completely rule out tiny exotic loopholes we have not discovered yet, but it makes aliens casually zipping around faster than light look extremely unlikely. So you are boxed in from all sides. rockets are crushed by the energy and mass requirements of relativistic flight. Warp drives and wormholes need forms of matter and energy we have never seen in usable amounts, and they threaten causality if you try to scale them up. The sky itself shows no sign that anyone else has found a workaround. And even if someone, somewhere did manage a local hack, the next problem is even bigger, because the universe is not just sitting there waiting for you. On the largest scales, space-time itself is stretching, and that expansion is steadily pulling most of the cosmos permanently out of reach. How do you even hope to catch anyone out there when the universe is literally stretching the floor under your feet and dragging most of the galaxies away from you faster and faster over time? On small scales, like inside the solar system or the Milky Way, gravity holds things together, so space feels stable. But on the really large scales, over hundreds of millions of light years, space itself is expanding. Galaxies are not flying through a static background. The actual metric of space is stretching, and the farther away a galaxy is, the faster it seems to recede from you. This is what Hubble's law is really saying. For every megaparsec of distance, about 3.26 million light years, the average recessional speed goes up by about 70 kilometers per second. So if a galaxy is 1 gigaparsec away, which is about 1,000 megaparsecs, or roughly 3.26 billion light years, its recessional speed is around 70,000 kilometers per second. That is already more than a fifth of light speed, almost a quarter. Push to 2 gigaparsecs. The speed doubles. In miles, you're talking tens of thousands of miles per second, entire galactic clusters sliding away at insane velocities. Not because they fired engines, but because new space is constantly appearing between you and them. If you keep going farther, you run into something that sounds wrong at first, but is absolutely real in standard cosmology. Beyond a certain distance, the recessional speed from expansion becomes greater than the speed of light. A galaxy far enough away is receding from you faster than c, not in the sense that it is moving through space that fast, but in the sense that the fabric of space between you and it is stretching so quickly that the distance grows by more than 1 light year per year. Relativity is not violated, because no object is locally outrunning light in its own neighbourhood, but globally the separation grows superluminally. For communication though, the technical detail does not help you. It means there are regions of the universe from which light, radio, lasers, anything emitted right now will never reach you, no matter how long you wait, and no matter how advanced the sender is. There is a real physical horizon set by expansion. Aliens beyond that horizon can build the brightest beacons in the universe, throw entire stars' worth of power into directed signals, and those photons will still never cross the growing gap to get here. They are not just far, they are causally cut off forever. Even inside the region, you can, in principle, see expansion still causes problems because it stretches the light itself. As photons travel through expanding space, their wavelengths get stretched, shifted toward the red end of the spectrum. This is cosmic redshift. A photon that left a distant galaxy as ultraviolet or visible light can arrive at Earth as infrared, or even microwave radiation. Early galaxies, where the first generations of stars burned, are now visible mainly in deep infrared, which is exactly why telescopes like JWST are built to see in those bands. Now think about technological signatures. A civilization's radio transmissions, optical lasers, ultraviolet emissions, all start at certain wavelengths. Over hundreds of millions or billions of light years, expansion steadily drags those frequencies downward. By the time they reach us, they can be smeared out, faint, and shifted into bands where we are not even looking, or where natural backgrounds are strong. In metric terms, a signal that began at a wavelength of a few centimeters might arrive stretched to meters. In daily language, their carefully tuned narrowband beacon gets turned into a stretched, weakened hiss buried in the long wavelength noise. So you get a double hit. Many galaxies are already beyond any possibility of contact because their recessional speed is effectively faster than light. Galaxies that are still inside the horizon can be so far away and so redshifted that even strong text signatures get washed into background radiation by the time they reach you. You might detect the host galaxy as a blob of infrared light. You might measure its star formation rate, its mass, its redshift, but any fine artificial structure sitting on top of that light can be lost. On top of that, the expansion is not slowing down. It is speeding up, driven by what we call dark energy. The more the universe expands, the more this energy dominates, and the faster distant regions are pulled away from each other. Over time, more and more galaxies cross a critical distance called the cosmic event horizon. That horizon is the boundary beyond which a light emitted toward you right now will never arrive, even if you wait for the entire future history of the universe. In Comoving coordinates, which track the large-scale grid of space, that horizon is tens of billions of light-years away. In simple terms, it sets the size of the bubble of the universe you can ever influence or hear from, even in theory. The key point is that this effective search volume is shrinking in practice. Right now you can see galaxies out to about 46 billion light-years in distance, because you're seeing light that left them long ago, when they were much closer. But the set of galaxies that can still send you new information, the set that is not yet over the horizon, gets smaller over cosmic time. The local group, your little cluster that includes the Milky Way and Andromeda, will stay bound together. Distant clusters will not. They are sliding away into permanent darkness from your point of view. That has a brutal implication for the search for aliens. The longer the universe runs, the fewer other galaxies are even in principle reachable by light-speed signals. The pool of possible communicators shrinks. Civilizations that form late in cosmic history will see a sky that looks emptier than yours, with fewer visible galaxies and fewer chances of contact. And even for you, today, most of the universe's volume is already either too far, too redshifted, or too delayed to matter for any live interaction. You're confined to a limited region in both space and time, and that region is not growing, it is effectively tightening. So even before you worry about how advanced any alien technology is, expansion itself has quietly erased most of your potential partners from the game board. They are either already beyond your horizon or on their way there. You are left searching inside a shrinking bubble, where distances are still enormous, delays are still crushing, and signals are being stretched and diluted the whole way in. And that leads to the next uncomfortable question. Even for the civilizations that are close enough, even for the ones that are still inside your horizon, can their signals actually stand out against all the natural noise and interference filling the universe, and against the way your own planet is changing how loud you are? How strong does a signal have to be before distance just grinds it down into nothing, no matter how good your receiver is? The moment you let a signal spread out in 3 dimensions, the physics starts killing it. When you broadcast in all directions, your power is smeared over the surface of an ever-growing sphere. As that sphere gets bigger, its area goes up with the square of the distance. Double the distance and the same total power is spread over 4 times the area. Make the distance 10 times bigger, and now the power per square meter has dropped by a factor of 100. So take a strong old-school TV transmitter on Earth, pumping out megawatts of power, blasting analog signals into space. At 1 light-year with a good receiver, that's not too hard to pick out. At 10 light-years, it's already getting thin. At a few hundred light-years, that same signal is spread over such a huge sphere that it is barely above the background hiss. In metric, the radius you care about goes from about 10 trillion kilometers to hundreds of trillions, and the signal strength per square meter drops by factors of hundreds or tens of thousands. In imperial, those are tens of trillions of miles turning into hundreds of trillions, and your original loud broadcast becomes a whisper, buried in static. Now add another problem. Earth is actually getting quieter to anyone listening from far away. In the mid-20th century, you blasted a lot of power into space without meaning to. Big analog TV transmitters, AM and FM radio, wide, sloppy signals going in all directions, high effective radiated power. Those were detectable from light-year distances with decent technology. Today, more and more of your communication has gone digital and directional. Data runs through undersea fiber cables, through tightly aimed satellite links, through low-power cell networks that hug the ground. Spread spectrum and frequency hopping techniques smear power out over many channels and time slots, which is great for efficiency and reliability, but bad for standing out to a distant eavesdropper. In precise terms, your effective isotropic radiated power, the power you would be putting out if you were broadcasting evenly in all directions, is probably going down over time. In plain language, the Earth used to shout into space, and now it mostly mutters into wires, waveguides, and narrow beams. To a listener 100 light-years away, mid-20th century Earth might look louder than early 21st century Earth, even though your actual technology is far more advanced. Just as you're starting to build serious instruments to listen for others, your own leakage is fading. But even if aliens are louder than you, and even if they are still using big, sloppy, powerful transmitters, their signals have to fight through a very busy universe. Space is not quiet. There is the cosmic microwave background, a radio-like glow from the Big Bang itself, sitting at a temperature of about 2.7 Kelvin. There is synchrotron radiation from charged particles spiraling in galactic magnetic fields. There is thermal emission from interstellar dust, from gas clouds from star-forming regions. On top of that, inside your own solar system, you have lightning storms on Earth, radio bursts from Jupiter, solar activity, and then a huge amount of man-made interference, satellites, radar, aircraft, ground transmitters. A narrow-band artificial signal coming from thousands of light-years away has to be strong enough and clean enough to rise above all that. It has to stand out against cosmic backgrounds and against your own junk. Your receivers have finite sensitivity and finite observing time. You can stare at one patch of sky and one frequency for a while, but you cannot stare at everything at every frequency all the time. So a distant civilization that is not beaming directly at you and not putting huge power into a tight channel will vanish into the noise before you ever notice it. You might say, fine, let's not rely on leakage. Let's assume smart aliens use focused beams, not broadcast towers. That is where lasers come in. With a high-powered laser and a good telescope, you can take a lot of energy and push it into a very narrow beam. That dramatically reduces the inverse square problem, because you're not wasting power in directions where nobody is. A laser beacon aimed straight at Earth could be detectable from thousands of light-years away, maybe more, with the right equipment and enough power. But as soon as you focus the beam, you trade away safety for accuracy. Now aim is everything. A planet like Earth is about 12,700 kilometers across, so roughly 10,000 to 20,000 kilometers is a round figure for a habitable target size. At a distance of just 100 light-years, that planet is a dot so small that your beam has to be insanely well pointed to hit it at all. A tiny error in angle, a fraction of a degree, means the beam sails past and never even clips the atmosphere. At 1,000 light-years, the aiming problem gets 10 times harder. In miles, you're trying to hit something maybe 8,000 to 12,000 miles wide over distances of hundreds or thousands of trillions of miles, and you do not get to correct mid-flight because the beam is just light, already on its way. So yes, laser beacons help with power, but they require either very precise knowledge of where your target is and where it will be centuries later, or a strategy where you sweep beams across huge patches of sky, over and over, burning staggering amounts of energy on the off chance that someone's telescope is looking at you at the right moment and frequency. If the beam misses Earth's orbit by even a fraction of a light year, we will never know it was there. To us, the sky stays silent. Put these pieces together and the picture is harsh. Isotropic broadcasts die very fast with distance because of geometric spreading. Our own accidental leakage is shrinking just as our ears are improving. The universe is filled with natural radio and microwave noise that buries weak, distant transmitters. Focused beacons can punch through some of that, but only if they are aimed at exactly the right place at exactly the right time. All of that sits on top of the speed of light limits you already heard about, and on top of the expansion of the universe pulling most galaxies out of reach. So even in the best case scenario, where aliens want to talk, have the power to shout, and know how to build tight beams and clever signals, the odds are stacked against easy detection. most signals decay into the background before they cross more than a tiny fraction of the galaxy. The few strong, well-aimed ones are like microscopic needles hidden in a pile of cosmic and human-made noise, and you can only search a tiny slice of that pile at any moment. That leads straight to the obvious question: given all these limits, all this noise and all this silence, what have decades of actual searches, the real SETI projects with real telescopes, really told you so far about how common loud, talkative civilizations actually are? How long do you have to listen to a silent channel before you stop expecting someone to talk? We've been pointing radio dishes at the sky for decades now, and the picture that's emerging is not friendly to the galaxy full of loud neighbours idea. Start with the basics. What have we actually done? The first serious attempt, Project Ozma in 1960, pointed a single radio telescope at a couple of nearby sun-like stars, listening at specific frequencies. Since then, the scale has grown. Arrays like the Allen Telescope Array and big programs like Breakthrough Listen have surveyed thousands of stars across billions of channels over several gigahertz of bandwidth. They look for narrowband spikes, signals that stand out sharply from natural noise. Every so often something interesting pops up, a signal that looks artificial at first glance. But every time so far, follow-up has killed the excitement. Either the signal doesn't repeat, or it's traced back to a satellite, an aircraft, a ground transmitter, or some natural astrophysical source. Right now, the best honest summary of the data is no obvious, continuous, loud cosmic radio beacons in your immediate neighbourhood. But that headline, "We haven't heard anything," is only part of the story, because the search volume is insanely huge. SETI researchers talk about the cosmic haystack, and they're not exaggerating. You're not just searching one dial on one radio, you have at least these dimensions: where in the sky you're pointing, what frequency you're listening at, how wide your frequency channels are, what polarization the signal might have, what kind of modulation it might use, how often it repeats, how long each transmission lasts, and when it happens. That is a multi-dimensional parameter space, not just a big field, but a whole grid of possible places a signal can hide. When people do rough estimates of how much of that haystack we've actually checked, the numbers come out brutal. Fractions like 1 in 10 to the 20th power or even smaller. Imagine searching a volume the size of Earth with a teaspoon and saying, "Haven't found gold yet." That is the level of coverage we're talking about. So on one hand, the silence is not surprising. We have not looked very deeply yet in a global sense. On the other hand, the fact that we haven't stumbled across anything easy, a screamingly bright, always-on beacon from a nearby star, does tell you something. If anyone close by is transmitting, they're either using very targeted beams, very short duty cycles, very low power, or they're just not doing it at all. Even when you don't find something, you still get information, because you can turn non-detections into limits. For example, look at the idea of a Kardashev Type 2 civilization, one that wraps its entire star in collectors, a Dyson sphere or swarm, to capture most of its power. That kind of structure would glow strongly in the infrared because it has to dump waste heat. Infrared sky surveys, like those done by the IRAS and WISE satellites, have scanned huge numbers of stars and galaxies, mapping out their spectral energy distributions. If Dyson spheres were common, we'd expect to see lots of stars with very strange infrared signatures, starlight missing in visible bands and re-emitted as smooth thermal infrared. We don't see that in any unambiguous way. There are dusty stars, there are weird systems, but when you model them with normal astrophysics, things like dust clouds and protoplanetary disks usually explain the data. That suggests that galaxy-wide, full-blown, energy-hungry megastructures are not common, at least not in the simple shell around a star form that would stand out against natural processes. So even at the extreme end, where civilizations try to grab as much power as possible, the sky is not full of obvious examples. Advanced species, if they exist, are either rare, subtle, energy efficient, or they build in ways that blend in with ordinary dust and gas. Pull back and connect this to the speed of light. You already know C sets a maximum speed for signals, and you've seen how distance and delay destroy any hope of quick conversation. Now layer on top the fact that in all the directions we've actually checked, over all the frequencies we've actually listened to, for all the stars we've stared at, we have not seen anything that screams, "Here we are," in a clear, repeatable way. That combination is nasty. It means that if advanced civilizations are out there, they're not broadcasting giant, continuous, obvious beacons in our local few hundred or few thousand light years. They're either extremely rare in space, extremely brief in time, extremely quiet in their emissions, or so far away that expansion and light speed delay have already pushed them into the category of never going to hear from them. In metric terms, think of a shell 1,000 light years thick around Earth, a region containing millions of stars. In imperial terms, that's a bubble trillions of miles across. If even a small fraction of those stars held civilizations that loved blasting omnidirectional radio, your instruments should already be tripping over signals. They're not. That does not mean there is no one, but it does mean that easy version of the story, crowded galaxy, lots of loud, long-lived, talkative species is not compatible with the data you have. So SETI plus the speed of light gives you a very harsh filter. Light speed ensures that signals take years to millennia to cross even local distances, and the actual surveys show no nearby civilizations compensating for that with huge, obvious transmitters. The result is that most advanced societies, if they exist, will be invisible to you in practice. They may be too far, their radio phase may be too short, their technology may be too efficient and quiet, or their signals may have passed Earth long before you had a chance to build telescopes. The universe does not just make aliens hard to reach, it multiplies every form of rarity, in space and in time, until almost everyone disappears behind light years of silence. And that brings you to the next level of bad news. Even if you assume life is not rare, even if you assume civilizations pop up quite often across billions of years, those civilizations themselves do not last long compared to cosmic time. They flare up, change their environment, talk for a while, and then vanish. When you put that on top of the speed of light, you get an even smaller overlap window, a tiny slice of time where two distant species are both alive, both technological, and both loud enough, at the right distance to ever notice each other. How long do you think your civilization has actually been visible to the universe? Not in terms of cities and empires, but in terms of signals another species could detect from light years away. When you line that up against cosmic time, the answer is basically no time at all. High-tech Earth, the version of your planet with industrial machines, electric grids, radio and spaceflight, is only about 200 years old. The universe is about 13.8 billion years old. That means your entire technological phase so far takes up roughly 1/70 millionth of cosmic history. In human terms, that is less than a blink. You are running a very brief experiment on a tiny rock and expecting the rest of the universe to notice right now. So think about searching for aliens in that context. Your serious radio leakage started in the early 20th century. Your targeted searches, like SETI with modern instruments, cover a few decades. Meanwhile, stars have been burning for billions of years. Planets have been forming, cooling, and evolving life on timescales of hundreds of millions of years. The odds that your current 100-year wide window lines up neatly with some other civilization's 100 or 10,000-year wide window are not great, even before you bring distance and light speed into the story. Now assume something moderately optimistic that a typical technological civilization, once it starts using radio and large-scale industry, lasts maybe 10,000 years before it collapses, changes into something quiet, or deliberately goes dark. 10,000 years sounds long compared to human recorded history, but it is still tiny next to the age of stars and galaxies. If that civilization is a few thousand light years away from you, then just the one-way light travel time is already comparable to, or longer than, its entire broadcast window. Their phase of being loud and detectable is like a thin, horizontal slice across their timeline, and your listening phase is a thin slice across yours. Most of the time, those slices do not overlap when you map them through light travel delays. Here is how that plays out. A civilization on the other side of the galaxy could have been broadcasting like crazy 50 million years ago. Their signals spread out as a growing bubble of radio and light. That bubble might have passed your location long before humans existed, or might still be tens of millions of years away, depending on their distance and when they started. From your point of view right now, the line of sight between Earth and that star is silent, not because they were never there, but because the timing is wrong. Their on period and your listening period do not line up once you factor in light speed. When people talk about the Drake equation, they often focus on n, the number of communicating civilizations in the galaxy right now. You can argue about the values of each term, how often life starts, how often it becomes intelligent, how long it broadcasts. You can get numbers from much less than 1 to many thousands. But even if n comes out bigger than 0, that does not automatically mean you will talk to anyone. What matters for you is not just how many civilizations exist, but how many pairs of civilizations are close enough at the same time, with enough overlapping broadcast and listening windows to see each other through the speed of light delay. In metric, you can think of this as an overlap probability problem. You have stars spread across tens of thousands of light years. You have lifetimes of technological phases, measured in thousands or tens of thousands of years at best. For any two randomly placed civilizations, you can calculate the light travel time between them, and then ask, did their weir-loud intervals overlap once you shift timelines by that travel time? In most random cases, the answer will be no. In plain language, it is like trying to sync two blinking fireflies on opposite sides of a huge city, when each firefly only blinks for a few minutes out of its entire life. And biology does not coordinate anything for you. Evolution does not care about synchronizing technology between worlds. It runs on local conditions over millions of years. On one planet, a mass extinction might wipe out complex life right before it was ready to go technological. On another, a stable climate might let intelligence rise earlier. Stellar activity, supernova radiation, asteroid impacts, plate tectonics, all of that changes the timing of when a planet is even capable of supporting advanced life, let alone radio-using societies. So the chance that your particular ascent to technology within the last couple of centuries lines up within a few thousand years of someone else's ascent and within a few hundred or a few thousand light years of distance is naturally small. Remember too that your own radio phase may not last that long. You're already shifting from loud broadcast towers to fiber and directional links. In another few hundred years, you might be almost radio silent at interstellar distances, even if your technology is far more advanced. The same could happen to others. They might move from noisy, wasteful systems to quiet, efficient, mostly wired or low leakage communications. So the part of their timeline where they are both active and detectable might be even shorter than their civilization's full lifetime. Put all of this together, and light speed becomes a multiplier on every bad factor. Limited lifetime plus big distances plus finite light speed means the number you care about, the number of mutually detectable pairs, not just n, but n that can see each other at the same time, is probably a tiny fraction of n itself. The universe could host many intelligent species over its full history, but their bright, noisy periods are scattered like a few thin threads through billions of years and across tens of thousands of light years. Most threads never cross. That leads to a very important point. The universe can be full of life and still look empty to you. There could have been civilizations in your own galaxy a billion years ago, building structures, sending shuttles, filling their local space with technology, all gone now. There could be civilizations that will arise a billion years from now, long after Earth is uninhabitable. Light speed ensures that your thin, approximately 10 squared to 10 to the 4th year window of technological visibility has to line up not only with their window, but also with the correct separation in space, or you never exchange a single bit of information. In that sense, your search is less like scanning a busy meeting and more like trying to catch one specific echo in a canyon, when the shout and the listener are separated by huge distances and by shifting walls. You're constrained both by when you exist and by how fast information can move. Change either one, and the map of who you could have met changes completely. But in this universe, time and sea are fixed. You get your tiny slot in history, your small radius of influence, and that is it. And even if you beat those odds, even if another civilization's brief noisy phase overlaps with yours in time and distance, you still have one more major obstacle. The universe is not a clean laboratory where artificial signals stand out perfectly. It is full of natural processes that can mimic or bury technological signatures, and over large distances, the same physics that makes stars shine and galaxies glow also works very hard to smear out, distort, and hide the fingerprints of alien industry. How do you tell the difference between a galaxy full of stars and a galaxy full of stars plus one species doing something insane with its energy use? On paper, big alien tech should be visible. In practice, normal astrophysics mashes those signals so hard that almost everything you can imagine building has a natural lookalike. Start with the classic idea, the Dyson sphere. Wrap a star in structures that collect most of its light, use that power, and then re-radiate the energy as waste heat. If the structures are roughly at room temperature, around 300 Kelvin, the peak of that radiation is in the infrared, not visible light. So your star stops looking like a bright point in optical wavelengths and starts looking like a warm, glowing object in the mid-infrared. Sounds straightforward. Look for stars that are dim or missing in visible light, but bright and smooth in infrared, and mark them as possible megastructure. The problem is, galaxies already glow like that. Dust grains floating between stars get warmed by starlight and radiate in the infrared on exactly the same temperature scale. Whole regions of star formation are full of dust and gas that soak up visible light and re-emit it as a broad thermal infrared glow. Surveys like WISE and Spitzer have scanned the sky and catalogued huge numbers of infrared sources. Their spectral energy distributions, the way brightness changes with wavelength, can often be explained with simple models that use dust, gas, and normal star populations. Separating one star wrapped in alien collectors from a compact dusty star-forming region is not trivial. You end up with a lot of ambiguous cases, and so far the boring explanations fit better. Then there are more targeted megastructure ideas, like giant shades that dim a star in patterns, or engines that slowly move a star by pushing on it. Those should cause strange light curves the way a star's brightness changes over time. We do see weird light curves. The poster child is Tabby's star, a star that showed irregular dips in brightness, not like a normal planet transit. For a while, the idea of alien megastructures was on the table as a speculative option. But as more data came in, the explanations that involve clouds of dust or complex intrinsic variability in the star itself looked more and more likely. Nature can give you dimming events, flickering chaotic patterns, all without any technology being involved. This keeps happening. You see an odd signal, you think, maybe tech. You collect more data, and you end up back at dust or gas or magnetic fields or instrument artifacts. The universe has a huge toolbox of ways to make light curve in messy ways, and it uses that toolbox all the time. A civilization building star-shading structures or orbital rings would have to stand out above that noise, either by having a very specific repeated pattern, or by being so extreme that it cannot be mimicked by dust or variability. So far, nothing has cleared that bar in a way that survives serious scrutiny. Now move to the high-energy side. Maybe advanced civilizations do not focus on starlight collectors at all. Maybe they build giant particle accelerators, or use antimatter reactors, or run fusion networks on a scale that pumps out gamma rays or neutrinos. Could you see that? In theory, yes, but the competition is brutal. The high-energy universe is already loud. Gamma-ray bursts release as much energy in seconds as your sun will release in its entire 10 billion-year life. Pulsars, magnetars, and active galactic nuclei throw out streams of high-energy photons and particles powered by whole stars falling into black holes, or by neutron stars with insane magnetic fields. These natural engines push out something like 10 to the power of 44 joules in very short times, far beyond anything a single planet-based civilization is likely to harness. So if you imagine an alien accelerator lighting up in gamma rays, it has to sit on top of a background where objects are already flinging out gamma-ray flashes across millions of light years. You're trying to pick out the signature of a lab experiment against a sky full of cosmic bombs. Even neutrinos, which are great for penetrating matter, arrive in floods from supernovae and remain incredibly hard to detect even from relatively nearby sources. A technological neutrino source at galactic distances would have to be absurdly powerful just to register as a bump over the baseline. Even if an alien tech signature manages to be strong enough locally, you still have the journey to worry about. Over cosmological distances, photons don't just cruise along quietly, they scatter off interstellar dust, they pass through clouds of ionized gas, they get absorbed and re-emitted. Their paths get bent by gravity. On top of that, expansion keeps stretching their wavelengths, slowly pulling them toward the red, lowering their energy. A laser that starts as a crisp, narrow line at 500 nanometers, a greenish optical wavelength, can be stretched into the infrared if it travels for billions of years in an expanding universe. In the lab, you can calculate exactly how far that shift goes, using redshift factors and precise wavelength relations. In simple terms, though, your nice, sharp, this is clearly artificial spectral feature gets dragged across the spectrum, broadened, and pushed into bands where there is more natural emission. The same goes for radio. Narrow band signals can be broadened by interactions with plasma and magnetic fields. Over thousands of light years, those small effects add up. Your carefully encoded hello starts to look less like a clean line on a graph and more like a small bump on top of a lot of messy background. So when you combine everything, natural infrared from dust, natural light curve weirdness, natural gamma and neutrino storms, plus scattering and redshift, you get a sky where artificial and natural signals are not separated by a clear border. The same physics that lets stars shine and galaxies form also acts like a distortion filter on any tech signature, bending it, stretching it, burying it. Tech has to be extremely large scale, extremely wasteful, or extremely cleverly modulated to stand out. And even then, the simple, boring astrophysical explanation often wins. That is the pattern you keep hitting again and again. Sci-fi promises that huge machines and wild energy use will light up the sky with obvious signs of intelligence. Real astrophysics says normal processes already produce most of the wild, bright, and chaotic behavior you can think of, and they do it with power levels that dwarf anything a single world could reasonably build. And when you add distance and expansion on top, even a real alien project gets blurred until it is just one more line on a busy spectrum. At this point, there is a tempting escape hatch people reach for. Maybe a small number of super advanced civilizations have gone beyond all this, cracked faster than light travel or communication, and they simply do not care about any of these limits. But that idea runs into one more brutal constraint. If anyone, anywhere, had actually broken the speed of light in a way that worked on large scales, your own physics would already be screaming about it. The universe you measure would look wrong. If anyone, anywhere, in this part of the universe had actually figured out how to send real faster than light signals, your physics would already be collapsing under the evidence. FTL doesn't just let aliens talk faster, it breaks the structure that all your precise systems depend on. Relativity says the speed of light in vacuum is the same for all observers, and that this value sets the upper limit for how fast cause can influence effect. The moment you let a signal outrun that, different observers moving at different speeds can disagree about which event happened first, and that disagreement shows up as measurable contradictions. Look at how tightly your own technology is chained to C being rock solid. Pulsars, rapidly spinning neutron stars, act as incredibly precise cosmic clocks. You time their pulses to microseconds, and their stability lets you test whether space-time is behaving as expected over thousands of light years. GPS satellites orbiting Earth have their clocks adjusted for both special and general relativity. If C were not constant, if signals could secretly outrun light in some directions or frames, the entire system would drift and fail. Optical interferometers, which combine light paths down to fractions of a wavelength, also rely on that constant speed. The fact that all these systems, from kilometre scales to astronomical scales, line up with the same speed of light to absurd precision is indirect but powerful evidence that there are no widespread FTL tricks happening in your local region. The deeper problem is causality. Relativity's math is very clear. If you allow any kind of signal to go faster than light in one frame, there will be other frames where that same signal travels backward in time. You can connect paths in space-time to form what are called closed time-like curves, loops where information or objects can, in principle, end up in their own past. That's not just a cute science fiction plot. It's a direct consequence of the geometry of space-time once you give up the light speed limit. If you can send a message into your own past, you can create paradoxes, situations where an event prevents itself from happening. Send a warning that stops the experiment that sent the warning. Destroy the conditions that led to your own existence. Your entire framework for quantum field theory, thermodynamics, information theory, all of it, quietly assumes that causes led to effects in a consistent order. Even statistical laws like entropy tends to increase rely on that directional arrow of time. If some advanced civilization somewhere nearby were constantly poking holes in causality with large-scale FTL, signaling or travel, the large-scale behavior of the universe would look different. You'd see violations in conservation relationships, weird correlations in high-precision experiments, timing mismatches that refuse to fit into relativity's structure. People often try to reach for quantum entanglement as a possible loophole, the famous idea that two particles can be linked so that measuring one instantly tells you something about the other, no matter how far apart they are. The key point here is that entanglement correlations are real, but they cannot be used to send usable information faster than light. The measurement outcomes are fundamentally random. You only see the correlation when you bring the data from both sides together later, using normal sublight communication. Physicists have tested this very carefully in so-called loophole-free Bell experiments, with detectors separated by kilometers, timed so that no slower-than-light signal could coordinate them. The correlations match quantum predictions, and they still do not allow FTL messaging. So entanglement is not an alien cheat code. It gives you strange statistical links, but not a way to encode and deliver "build this" or "we are here" faster than light. Any civilization relying on entanglement for conscious signaling would hit the same wall you do. They can exploit quantum mechanics to make better cryptography, better sensors, better computing, but when it comes to sending a bit from point A to point B, they are stuck with light speed or slower. That brings you to the last important point in this chain. Even if ultra-advanced aliens exist, they still live in this universe, not a custom one. They see the same cosmic microwave background you do, a relic glow at about 2.7 Kelvin. They see the same patterns in element abundances, showing that hydrogen and helium formed in the Big Bang, with traces of heavier elements built in stars. They see the same particle zoo in their accelerators, the same constraints on forces and symmetries. They might have gone further than you, maybe they've unified more forces, maybe they've discovered new particles, maybe they understand why the speed of light has the value it does as an emergent property of deeper laws. But understand why is not the same as can ignore. Knowing the reason a wall exists does not let you walk through it. If C is a fundamental limit baked into space-time geometry or an emergent limit from some deeper quantum structure, then it applies to everyone, everywhere. You don't get a special exception just because your species is older or smarter. Aliens could have more accurate theories, better approximations, more powerful tools, but their ships and signals are still in the same metric, the same expanding space-time, with the same light cones defining what can talk to what, and when. And that is the real trap. You cannot just wave your hands and say, maybe they found a way around it, without also accepting that such a way around it would shatter the success of all the physics we test every day. If FTL were in regular use by anyone in our region of the universe, The structures you rely on, from pulsar timing arrays to gravitational wave detectors, would be screaming about inconsistencies. They are not. They keep reinforcing the same picture over and over. C is a hard limit for information and causal influence. So when you put it all together, FTL is not just missing from your toolkit, it's missing from the behaviour of the universe itself. No holes in causality, no timing anomalies in remote events, no evidence of signals outrunning light. That closes off the easy escape from the light-speed prison. You are stuck playing the game with distance and time exactly as they are, with no warp button, no quantum backdoor. And once you accept that, you have to confront one more layer of hostility in the setup. Because even if you stick to sublight physics, even if you build the best telescopes and receivers you can, the universe is not passively sitting there waiting to be transparent. The medium between stars and galaxies, the very structure of the Milky Way, actively hides and distorts information, turning space into a kind of permanent fog that works against every attempt to see clearly or to be seen. You're not just fighting distance and light speed, you're also fighting the fact that the universe itself behaves like it's trying to hide the things from you. Space between stars looks empty to your eyes, but physically it is not empty at all. The interstellar medium, the stuff between stars, has gas at densities of a few atoms per cubic centimetre, plus dust grains made of heavier elements. That sounds thin, but stretch it out over thousands of light years, and it becomes a real obstacle. At visible wavelengths, that dust scatters and absorbs starlight. Whole regions of the Milky Way's disk are effectively opaque in optical light, dark lanes where your telescopes just see black. Anything behind those curtains, including planets, cities, or beacons, is simply not visible in that band. Radio waves do better. They can penetrate dust much more effectively, which is why SETI work usually focuses on radio frequencies. But even radio is not perfectly clean. As signals move through plasma, the ionized gas between stars, they get dispersed. The lower frequencies are delayed more than the higher ones, stretching out sharp pulses into smeared signals. Scattering off small-scale density fluctuations can also blur and broaden features. Over hundreds or thousands of light years, a crisp, narrow signal can be smeared out in time and frequency, making it harder to distinguish from background noise. So even in the best part of the spectrum for long-distance communication, the medium keeps degrading the clarity of whatever is sent. Then look at your own galaxy as a background source. The plane of the Milky Way, the band you see across the sky, is full of emission across many wavelengths. Hydrogen atoms emit at specific radio lines when electrons change energy levels. Cosmic rays spiral along magnetic field lines and produce synchrotron radiation. Dust clouds warmed by starlight emit thermal radiation, especially in the infrared and microwave bands. In precise terms, you can write down spectral flux densities in units like watts per square metre per hertz, and you see a complicated spectrum with lots of components. In plain terms, the galaxy is loud and messy. Trying to pick out a weak, narrowband alien signal against that is like trying to hear a soft voice in a busy airport, except the airport is 10,000 light years wide and full of different languages all talking at once. SETI researchers talk about cosmic waterhole bands, frequency ranges where natural sources are relatively quiet and the atmosphere is transparent, like around the hydrogen line at about 1.4 gigahertz. Those are good hunting grounds, but even there you have man-made interference, satellite transmissions, radar, plus residual galactic noise. There is no truly quiet channel. Everything is competing with something else. On top of that, light does not travel in straight, simple lines once you start including gravity at large scales. Mass warps space-time, so light rays from distant objects can be bent as they pass near galaxies and clusters. This is gravitational lensing. For astronomy, lensing is useful. It can magnify distant galaxies and let you see fainter objects than your telescope could otherwise detect. But from a signalling and interpretation perspective, it introduces confusion. A hypothetical alien beacon sent from a source behind a massive cluster could be bent into multiple paths. You might receive several images of the same signal, coming from slightly different positions on the sky, and arriving at different times because the light paths are different lengths. That means a single artificial transmission could show up as a set of pulses separated by days, years, or more, distorted in strength and shifted in angle. If you do not know there is a lensing mass in the way, you might misinterpret a lensed, repeated signal as multiple unrelated events, or you might never realize they share a common origin. Localizing the transmitter, figuring out where the beacon actually is, becomes a lot harder when space-time itself is acting like a glass lens with imperfections you have to model. Go even closer to extreme objects and the situation gets worse. Near black holes and dense neutron star clusters, space-time curvature is so strong that light can orbit, get trapped, or be redshifted to much longer wavelengths. If a civilization chooses to live or build near the center of a galaxy, where there are many black holes and dense stellar populations, the environment is hostile to clean signal propagation. Photons can be swallowed, scattered, or shifted down in energy until they blend into the background. The same extreme gravity that makes those regions interesting for energy and exotic physics also makes them information sinks. Signals trying to climb out can be stretched and weakened, and some paths never escape at all. Compact objects do not only bend light, they also shape the plasma and magnetic fields around them. Jets, winds, and accretion flows churn the environment. Any artificial radio or optical signals have to fight against that noise. From far away, your instruments see a chaotic, flickering region with flares, bursts, and variable emission that can mask or mimic technological activity. If aliens are using those environments as power sources, their tech signatures may be buried inside the mess of natural variability from accretion disks, jets, and magnetic reconnection events. So to summarize the situation you're actually in, the interstellar medium blocks and smears signals in some bands. The galaxy itself is a bright, complicated background at many frequencies. Gravity bends and delays light, breaking your simple straight line assumptions. Extreme regions around black holes and compact objects actively eat and scramble information. All of that sits on top of the inverse square law, the redshift from expansion, and the finite speed of light. The combined effect is that the universe behaves less like a clean laboratory and more like a battlefield covered in smoke, glare, and echo. You're trying to detect faint, artificial patterns through a medium and background designed by physics, not for clarity, but for whatever local conditions happen to form. Even robust alien attempts to be seen can end up degraded, deflected, absorbed, or embedded in noise. And there's one more twist. While all of this tells you that long-distance contact is extremely hard, you still see plenty of claims down here on Earth that say the opposite, that aliens are already visiting, casually hopping between stars, ignoring every single limit you've just walked through. So the next question is unavoidable. If the universe is this hostile to interstellar contact, what does that say about stories of visiting UFO aliens, dropping in for quick trips to one random planet? How do claims of aliens dropping by for quick visits survive even a basic look at the numbers you've just walked through? In a lightspeed universe, interstellar tourism is not a casual activity. It's a multi-decade to multi-million-year commitment. Even if some civilization builds ships that can cruise at a significant fraction of light speed, say 0.5 c to 0.9 c, the timescales are brutal. A run to a nearby star a few light years away still means years to decades of ship time, depending on acceleration and deceleration profiles, and decades to centuries of time passing back home. Once you talk about crossing thousands of light years, the rough scale of the Milky Way, even optimistic near-sea travel, translates into tens of thousands to millions of years in the external frame. So any story where a species casually hops over from some distant part of the galaxy, visits Earth, then zips back home for the weekend is flatly incompatible with that math. At sublight speeds, a round trip across the galaxy is not a trip, is essentially an evolutionary era. population, language, even biological form. All of that would have time to mutate beyond recognition while the ship is in flight. Time dilation at near sea helps the travellers. They might experience less time on board, but it does nothing to reduce the elapsed time in the galaxy's frame. The rest of the universe still waits the full thousands or millions of years. Now think about what it takes to have a civilization that routinely does this on a large scale. Moving starships around the galaxy at relativistic speeds is not a hobby. You need ridiculous amounts of energy and infrastructure. You're talking about beamed power networks spanning entire planetary systems, perhaps multiple stars. You're talking about large-scale starlifting, harvesting stellar material to fuel huge engines. You're talking about Dyson swarms, dense shells, or swarms of collectors around stars, pushing their luminosity into waste heat infrared signatures. A species that has the economic and technological capacity to throw ships around the disk of the Milky Way like airplanes would almost certainly reshape the energy budget of its region. That sort of activity wouldn't be invisible in surveys. Infrared telescopes like WISE and Spitzer look at how galaxies radiate across the spectrum. A galaxy where a single species is dominating many stars, building megastructures and running intense power networks would likely show up as having unusual infrared excess, strange stellar populations, or obvious deviations from normal galactic energy distributions. So far, when astronomers look across thousands and tens of thousands of galaxies, they do not see a clear example that screams, one civilization is carving its will into these stars. The Milky Way in particular looks like a normal spiral galaxy in terms of its light output, not like a machine that's been heavily modified by a Kardashev Type 3 empire. At the same time, down on Earth, you have UFO stories and UAP debates. From a strict reasoning point of view, you have to compare explanations. On one side, you have misidentified aircraft, drones, atmospheric phenomena, sensor glitches, software bugs, classified human tech, and social factors like hoaxes and misperception. All of those are known to exist, happen often, and fit well inside current physics. On the other side, you have aliens broke the speed of light, can cross tens or hundreds or thousands of light years on demand, and then choose to play hide and seek with one primate species on one planet. When you weigh those possibilities, the second one is not just unlikely, it collides head-on with everything your astrophysical data says. Cosmic rays, supernovae, pulsar timing, gravitational waves, CMB measurements. All of that points to a universe where C is a hard wall. Any theory that assumes routine FTL travel or mass interstellar commuting has to ignore that wall or rewrite it. So as soon as you hear a claim that requires aliens casually bypassing light speed, you're not just adding an extra detail, you're throwing out an entire extremely successful physical framework and replacing it with they can do magic that somehow never leaves a trace in any of your precision measurements. So if you force yourself to stay honest and still allow the possibility of non-human intelligence, you end up in a different place entirely. If something non-human is here now, interacting with Earth, the simplest way to make that compatible with light speed constraints is to assume it is local. Maybe it arose here in the deep past and survived in some hidden form. Maybe it is synthetic, built by human or pre-human processes. Maybe it lives in the solar system, in places you have barely explored, like deep subsurface oceans, asteroids, or the outer regions. None of that requires breaking sea. None of that demands galaxy-spanning travel. It is all local weirdness, not tourists from thousands of light years away. But notice what that does to the original romantic idea. It turns galactic visitors into neighbours you never noticed, which might be interesting as a separate story, but it doesn't help you with the question this whole chain is about. Can you contact civilizations out there across interstellar or intergalactic distances? For that problem, for true interstellar aliens, the speed of light remains the killer constraint. It blocks casual travel, it stretches out communication, it makes large-scale tourism and policing implausible, and it forces any realistic scenario back into slow, expensive and rare expeditions, if any exist at all. So you're left with a very stripped-down picture. Either the UFO reports are explained by local mundane causes, or, in extreme cases, by some form of local non-human intelligence that does not need to cross the galaxy. In none of those scenarios do you get a universe where advanced civilizations are routinely visiting multiple worlds across the Milky Way for quick meetings. The lightspeed universe you actually live in simply does not support that kind of traffic. And when you finally step back from all of this and ask, what does the long-term future of this situation look like? The answer gets even colder. Because over billions of years, as dark energy keeps driving expansion and the more galaxies fall over the horizon, you are heading toward a cosmic endgame where not only is it hard to find aliens, the very structure of space-time locks every remaining island of life into permanent isolation. There is a point in the universe's future where, even if it's full of life, nobody anywhere can ever reach anyone else again, no matter how advanced they are. The physics you've been walking through doesn't just make contact hard now, it pushes everything toward a final state where contact is literally impossible. Dark energy is what drives that. On the largest scales, it makes expansion not just continue, but accelerate. Gravity still wins locally, so structures that are tightly bound, like your local group of galaxies, stay glued together. The Milky Way, Andromeda, and a few dozen smaller galaxies will eventually merge into one big remnant over the next few billion years. But everything beyond that little island, all the other galaxies you see in deep field images, only slides away faster and faster. In a few tens of billions of years, an observer living in that merged Milky Way Andromeda system will look up and see almost nothing beyond their own halo of stars. No big spiral neighbours, no distant clusters, just a dark skill with a few faint relics fading at the edge. Right now, your observable universe has a radius of about 46 billion light-years, even though the universe itself is only about 13.8 billion years old. That number is bigger than age times c, because space has been expanding while light travels, stretching the distances. In metric, you say 46 billion light-years of proper distance today. In more intuitive terms, that's the furthest edge of the bubble from which light has had time to reach you since the Big Bang. But there is a more important boundary, the event horizon, the maximum distance from which light emitted now can ever reach you in the future. That horizon corresponds to a comoving distance of only tens of billions of light-years, and as time passes, more and more galaxies you currently see will cross that line. So your observable universe, in the sense of stuff whose current state can ever affect you, shrinks in practice. Everything not gravitationally bound to your little island drifts beyond the final call radius. Even if some civilization out there waits and tries to send a last signal, that signal will never get through. The space between you and them is expanding too fast. What counts as reachable is not everything inside 46 billion light-years, it is everything inside the event horizon, and that set gets smaller in terms of who can still talk to whom as the expansion accelerates. Now think about what that does to future astronomers. Today you can still see the cosmic microwave background, a faint glow at about 2.7 Kelvin, stretched relic light from when the universe was only a few 100,000 years old. You can see galaxies at many different distances, and by measuring their redshifts you can reconstruct that the universe was smaller and denser in the past. That's how you know there was a Big Bang, that the universe has a history, that it evolves with time. But as expansion continues, the wavelengths of that background radiation keep stretching. Eventually the CMB gets redshifted so far that it moves into absurdly long wavelengths, far beyond the sensitivity of any realistic detector. It becomes effectively undetectable. At the same time, the galaxies not bound to your local group keep receding. Their light gets fainter, more redshifted, harder to pick out from local noise. One by one, they pass over the event horizon. After enough billions of years, an intelligent species living in the Milky Way Andromeda remnant would see only their own galaxy, maybe a few tightly bound companions, and nothing else. No Hubble flow, no pattern of redshifts, no microwave background, no external anchors to tell them that space-time is expanding. Their best fit model would probably be a static or nearly static universe, containing just their own system of stars. So the window where you can even know that the universe is large and expanding is temporary. You live in a special era where the CMB is still visible, where plenty of external galaxies are still on your side of the horizon, where the clues are still on the sky. Future civilizations, if any, may be locked into a tiny observational bubble and never realize that almost everything that could have been a partner in communication has already slipped away beyond their reach. Now stack this endgame on top of everything else you've walked through. You have C as a strict speed limit. You have distances measured in trillions of kilometers and millions of light years. You have signal strength dropping with the square of distance, noise and backgrounds drowning out weak transmissions, dust and gas scattering and smearing whatever gets through. You have relativistic energy costs turning starships into flying fuel depots. You have wormholes and warp drives that, as far as real physics is concerned, need exotic matter we've never seen and threaten causality if scaled up. You have civilizations whose technological phases are razor-thin slices compared to cosmic time, most of them never overlapping after you include light travel delays. And finally, you have dark energy steadily cutting the universe into isolated gravitational islands that will never be able to talk to each other again. The result is not just aliens might be rare. The result is that even if they are common over the full history of the universe, the odds that any two of them ever find each other, talk in real time and keep that conversation going are incredibly low. The geometry of space-time, the way distances, time and expansion work together, is actively hostile to contact. The speed of light doesn't just slow your search, it defines the boundaries of who can ever be aware of whom, and for how long. It takes every kind of rarity in space, rarity in time, rarity in loudness, and multiplies it into near invisibility. So when you look up and see a silent sky, the most unsettling conclusion is not that you're alone, it's that the universe is built in a way that almost guarantees mutual isolation. You and almost all aliens that ever exist could live entire histories, reach incredible levels of technology, and die out again, all without ever knowing for sure that the others were there. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video, and subscribe to the channel for more such amazing videos.